The duodecimal system, a different take on the number of digits we can use. So right now we use a decimal system, which is 10, and this was probably chosen, it is theorized because we have 10 fingers, so it was really just an arbitrary choice to use 10 as our base. But many people are a proponent, I don't know about many, but people are a proponent of the duodecimal system, and this system uses a base of 12. And there's even a society called the Duodecimal Society of America that is dedicated to educating the public on a duodecimal system. And I think they could probably do a cooler logo, honestly. But nonetheless, there is an entire organization and a nonprofit dedicated to helping educate those to the duodecimal system. The challenge is we have been trained since we were 3 years old, which, by the way, is a divisor of 12, and it is extraordinarily difficult to transition to a different base. In fact, we use a base of 2, 8, a base of 16 in computers, in computer science, but everything else is a base of 10. But there's the case to be made that a base of 12 is actually more efficient because it's easier to divide 3, 4, and 6 into 12. Not easier. You are able to divide 3, 4, and 6 into 12. Whereas in 10, you can only divide 5 into 10. And so that's why you might see dozens, the measurement of dozens used quite frequently. And 12 is used in feet, so you have 12 inches. 12 is used in eggs, a dozen eggs. 12 is used in months. We have 12 months in a year. It is used in hours. We have 24 hours in a day, but it's usually shown on the clock as 12 and 12. And then 360 degrees in a circle, which is just 12, 120 3 times, 12, 10 times. So you can see that 12 pops up all over the place in our measurement, in our units, the unit of measurement. And so the case can be made for a duodecimal system. But what exactly is a duodecimal system? And to understand that, we have to understand base 10 just means we have 10 digits to pick from. We have 1, we have 0, I almost forgot, 2, 3, all the way to 9. This is base 10. We have 0 to 9, 10 digits to choose from to form any integer or any number we want, like 859 or 743. We can use these 10 digits to form any number. With a base of 12, we have 2 additional digits to choose from. So we have 0, 1, 2, all the way to 9 like before. But now we have 2 more digits, and we use a chi, the Greek letter chi, and the Greek letter epsilon. And there we have 2 more digits to choose from. And the chi is pronounced del, and the epsilon is pronounced L. And so, if we are forming a number using these additional digits, for example, we would have deltine and ltine, and then 20. And so you have deltine, you have ltine, you have 20. You can go through all of the numbers again, and you get, let's say, 20 del and 20 L, and then finally you're at 30. And so you can see how this might be very confusing when you are attempting to do multiplication or division. And so the transition is very difficult, which is why it would require an incredible effort to relearn a new base and perform and memorize the multiplication table for it and be able to logically work through division using them and thinking about fractions using del and l. It is just mind-boggling difficult to do so if you've already mastered the decimal system. However, if we made a dramatic educational reformation and started teaching children from the age of 3 the duodecimal system instead of the decimal system, it would be quite straightforward. It would be just like learning the decimal system for them, but not for us. It's analogous to transitioning the entire transportation grid to electricity instead of a combustion engine. It requires decades of policies, decades of infrastructure building, and commitment by the people to move away from something they're familiar with and mastered their entire life into something completely different. And there will always be a subset of people that refuse to change, even if it's more efficient. And so the duodecimal system versus the decimal system. Also, duodecimals are called the Duodecimal Society. Duodecimal meaning dozens. I'm not a huge fan of that name. I like duodecimal better. That is a great summary of it. To make it more clear, I'll write out base 12 and base 10. So base 12. So L is equal to 11. L is equal to 11. Del is equal to 10. And so deltine. And so yeah, this is a better breakdown of what it would look like. And then here we can see how complicated it gets. This would be normally 170. This would normally be 170, but it's 148. We have the chi times 1755 gives us 14,000. And then we can even see how difficult fractions become to conceptualize. So n equals 2. 1 over 2 is 0.6 instead of 0.5. 3. 1 over 3 is 0.4. 1 over 4 is 0.3. 1 over 5 is 0.2497, repeating. And so you can see just how different everything becomes by operating at a different base. It would require an immense amount of effort to be able to master a new base like the duodecimal system. And with that, we'll see you in the next video.